Sir, we can start, sir. Now. Ramesh, sir.
Sir, good evening. Dr. Ayappan sir, ತಾವು introduce ಮಾಡ್ತೀರಾ? At the outset, I welcome our Honorable Chairman, Professor S. Ayappan, and our esteemed KSTA member, Dr. Basuraj Mulimani sir, former Vice Chancellor of Gulbarga University, and today's speaker, Dr. Thejaswi Umanath Tumkur, for this webinar, and also all the participants. Now I request our Honorable Chairman to introduce the speaker to the audience. Over to you, sir.
Thank you very much. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಕರ್ನಾಟಕ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿಯ ರಾಜ್ಯವ್ಯಾಪಿ ಪ್ರತಿಭಾ ಶೋಧ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ತಜ್ಞರಿಂದ ಉಪನ್ಯಾಸ ಮಾಲಿಕೆಗೆ ನಿಮ್ಮೆಲ್ಲರಿಗೂ ಸ್ವಾಗತ. ಇವತ್ತಿನ ಅತಿಥಿ ಉಪನ್ಯಾಸಕರು ಅಮೆರಿಕದ ಕ್ಯಾಲಿಫೋರ್ನಿಯಾದಲ್ಲಿರುವ ಲಾರೆನ್ಸ್ ಲಿವರ್ಮೋರ್ ನ್ಯಾಷನಲ್ ಲ್ಯಾಬೊರೇಟರಿಯಲ್ಲಿ ರಿಸರ್ಚ್ ಸೈಂಟಿಸ್ಟ್ ಆಗಿ ಕೆಲಸ ಮಾಡ್ತಿರುವ ಡಾಕ್ಟರ್ ತುಮಕೂರ್ ಉಮಾನಾಥ್ ತೇಜಸ್ವಿ ಅವರು. ಇವತ್ತು ನಿಮಗೆ ಈ ಮೀಟಿಂಗ್ಗೆ ಸ್ವಾಗತ. ಮತ್ತೆ ಹಾಗೆ ನಮ್ಮೊಟ್ಟಿಗೆ KSTA ಸದಸ್ಯರಾದ ಪ್ರೊಫೆಸರ್ ಬಸವರಾಜ್ ಮೂಲಿಮನಿ ಅವರಿದ್ದಾರೆ. ನಿಮಗೂ ಕೂಡ ಸ್ವಾಗತ ಸರ್. ನನ್ನ ಜೊತೆ ನಮ್ಮ ಸಹೋದ್ಯೋಗಿಗಳಾದ ಡಾಕ್ಟರ್ ಎಂ ರಮೇಶ್, CEO, ಶ್ರೀ ಉಮೇಶ್ ಮತ್ತಿತರರು ಜಾಯಿನ್ ಆಗಿದ್ದಾರೆ. ಹಾಗೇನೆ ಇದನ್ನ ವೀಕ್ಷಿಸುತ್ತಿರುವ ನಮ್ಮ ವಿದ್ಯಾರ್ಥಿಗಳು ಇದರಲ್ಲೂ ನೋಡ್ತಾ ಇದ್ದಾರೆ, ಮತ್ತೆ ಯೂಟ್ಯೂಬ್ ಅಲ್ಲಿ ಕೂಡ ತುಂಬಾ ಜನ ನೋಡ್ತಾರೆ. ಎಲ್ಲರಿಗೂ ಸ್ವಾಗತ. ಒಂದು ಸ್ಥೂಲ ಪರಿಚಯ ಡಾಕ್ಟರ್ ತೇಜಸ್ವಿ ಅವ್ರದ್ದು. ಅವರು ಹೆಸರು ಹೇಳೋಗೆ ಡಾಕ್ಟರ್ ತುಮಕೂರ್ ಉಮಾನಾಥ್ ತೇಜಸ್ವಿ ಈ ರಾಜ್ಯದವರೇ. 3 ಪದವಿಗಳನ್ನ 3 ಡಿಗ್ರಿಗಳನ್ನ BS, MS ಮತ್ತು PhD ಅಮೆರಿಕಾದಲ್ಲೇ ಹೊಂದಿರುವ ಒಂದು ಅಪರೂಪ ವಿಜ್ಞಾನಿ. BS ಬಂದು ಪರ್ಡ್ಯೂ ಯೂನಿವರ್ಸಿಟಿಯಿಂದ, MS ಮತ್ತೆ PhD ನಾರ್ಫೋಕ್ ಸ್ಟೇಟ್ ಯೂನಿವರ್ಸಿಟಿಯಿಂದ ಪಡೆದು ಫಿಸಿಕ್ಸ್ ಅಲ್ಲಿ ನಮ್ಮ ಬಸವರಾಜ್ ಮೂಲಿಮನಿಯವರು ಕೂಡ ಈಸ್ ಆಲ್ಸೋ ಎ ಫಿಸಿಸಿಸ್ಟ್. ಸೊ ಇವತ್ತು ಭೌತಶಾಸ್ತ್ರದಲ್ಲಿ ಒಂದು ಹೊಸ ಆಯಾಮದ ಬಗ್ಗೆ ಡಾಕ್ಟರ್ ತೇಜಸ್ವಿ ಅವರು ಮಾತಾಡ್ತಾರೆ. ಡಾಕ್ಟರ್ ತೇಜಸ್ವಿ ಅವರು ಅದಾದ್ಮೇಲೆ ಆಸ್ಟ್ರೇಲಿಯನ್ ನ್ಯಾಷನಲ್ ಯೂನಿವರ್ಸಿಟಿಲಿ ಅಲ್ಲಿ ಕೆಲಸ ಮಾಡಿದ್ರು ಆಸ್ ಎ ವಿಸಿಟಿಂಗ್ ಸ್ಟೂಡೆಂಟ್, ಆಸ್ ಎ ವಿಸಿಟಿಂಗ್ ಸೈಂಟಿಸ್ಟ್, ರಿಸರ್ಚರ್. ನಾರ್ಫೋಕ್ ಸ್ಟೇಟ್ ಯೂನಿವರ್ಸಿಟಿ ಗ್ರಾಜ್ಯುಯೇಟ್ ರಿಸರ್ಚ್ ಅಸಿಸ್ಟೆಂಟ್ ಆಗಿದ್ರು. ಮತ್ತೆ ಅಮೆರಿಕಾದಲ್ಲಿ ರೈಸ್ ಯೂನಿವರ್ಸಿಟಿಯಲ್ಲಿ ಪೋಸ್ಟ್ ಡಾಕ್ಟರಲ್ ಫೆಲೋ ಆಗಿ ಕೆಲಸ ಮಾಡಿದ್ರು. ಆಮೇಲೆ ಫ್ರಾನ್ಸ್ ಅಲ್ಲಿ ಕೂಡ ಯೂನಿವರ್ಸಿಟಿ ಆಫ್ ಸ್ಟ್ರಾಸ್ಬರ್ಗ್ ಅಲ್ಲಿ ಪೋಸ್ಟ್ ಡಾಕ್ಟರಲ್ ರಿಸರ್ಚರ್ ಆಗಿದ್ರು. ನಾ ಹೇಳಿದಾಗೆ ಈಗ ಕ್ಯಾಲಿಫೋರ್ನಿಯಾದ ಲಾರೆನ್ಸ್ ಲಿವರ್ಮೋರ್ ನ್ಯಾಷನಲ್ ಲ್ಯಾಬೊರೇಟರಿಯಲ್ಲಿ ರಿಸರ್ಚ್ ಸೈಂಟಿಸ್ಟ್ ಆಗಿದ್ದಾರೆ. ಅವರ ಪ್ರಬಂಧಗಳು ಹಲವು ಅಂತಾರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ಪತ್ರಿಕೆಗಳಲ್ಲಿ ಪ್ರಕಟವಾಗಿವೆ. ನಂಬರ್ ಆಫ್ publications in international journals. He is also awarded the Outstanding Graduate Student Award in the Norfolk State University, the fellowship there, and also the postdoctoral fellowship at Rice University, and the first place winner in the present laboratory for his assessment of why research is important. ಇದೆಲ್ಲದರ ಜೊತೆಗೆ ಅವರು ನಮ್ಮ ಆಹ್ವಾನ ಸ್ವೀಕರಿಸಿ ಬಂದಿದ್ದಕ್ಕೆ ತುಂಬಾ ಥ್ಯಾಂಕ್ಸ್, ನಮ್ಮ ಧನ್ಯವಾದಗಳು. And then with these words, I would like to welcome Dr. Thejaswi for his talk on light matter interactions, the marvel of light matter interactions at nanoscale. Nanoscale ನಲ್ಲಿ ಬೆಳಕು ಮತ್ತು ವಸ್ತುಗಳ ಪರಸ್ಪರ ಕ್ರಿಯೆಯಲ್ಲಿ ಉಂಟಾಗುವ ಅದ್ಭುತ ಸೋಜಿಗಳು. ಇದ್ರ ಬಗ್ಗೆ ಕನ್ನಡ ಇಂಗ್ಲಿಷ್ ಎರಡು ಮಿಕ್ಸ್ ಮಾಡಿ ಮಾತನಾಡಬೇಕು ಅಂತ ಕೇಳ್ಕೊತೀನಿ. I once again thank you and request you, Dr. Thejaswi, for your talk. Over to you, Dr. Thejaswi.
Namaskara elrigu. Dr. S. Ayappan, thank you so much for that very kind introduction. Thank you also nimge illi invite ಮಾಡಿದ್ದಕ್ಕೆ ನನ್ನನ್ನ. Thanks also to Dr. Ramesh as well for organizing the event and facilitating this all. ಈ ಫೋರಮ್ ಅಲ್ಲಿ ಮುಂಚೆ ಮಾತಾಡಿರೋ ಸ್ಪೀಕರ್ಸ್ ನಾನು ನೋಡಿದೆ, ಅವ್ರ ಟಾಕ್ಸ್ ನ ಕೇಳಿದೆ, ಅಂಡ್ ಇಟ್ ವಾಸ್ ರಿಯಲಿ ಇಂಪ್ರೆಸಿವ್ ಅಂಡ್ ಇಟ್ಸ್ ರಿಯಲಿ ಹಂಬ್ಲಿಂಗ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಫಾರ್ ಮೀ. ಅಂತವ್ರ ಮುಂದೆ ನನಗೂ ಈ ಆಪರ್ಚುನಿಟಿ ಕೊಟ್ಟಿರೋದು. ಸೊ ರಿಯಲಿ ಅಗೇನ್ ಎಕ್ಸ್ಪ್ರೆಸಿಂಗ್ ಮೈ list of gratitudes to you. ಸುಮಾರು ಟರ್ಮ್ಸ್ ಎಲ್ಲ ಇಂಗ್ಲಿಷ್ ಅಲ್ಲಿ ಇರೋದ್ರಿಂದ ಮೋಸ್ಟ್ ಆಫ್ ಮೈ ಟಾಕ್ ಇಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಇನ್ ಇಂಗ್ಲಿಷ್, ಬಟ್ ಏನಾದ್ರು ಪ್ರಶ್ನೆಗಳಿದ್ರೆ ಐ ರಿಯಲಿ ಬಿ able to answer them in Kannada as well. So with that, I'd like to thank you all for being here. And as you can probably guess from the title of my talk, it deals with the topic of light matter interactions, specifically optical materials at the nanoscale. And it's meant to be a more or less broad, high-level overview of the field of optical materials. So this is in no way extensive, or it's not all-inclusive. Sumar nanu works na what I'll be presenting today. Sumar research groups madiro kelskalidu, hundreds or even thousands of researchers. And I'm just going to summarize the essence of some of these contributions that have been done in this field over the last 20 years or so. So I'll first start by going over some fundamentals of electromagnetic waves, some fundamentals of material science, as a backdrop to two exemplary applications in metamaterials and so-called plasmonic materials. And at the end of the talk, my goal is really to convince you that this is a very nice and interesting space to work in. It's also something one can build their career upon. It's a lot of room for fundamental science as well as working on developmental aspects on some real applications. So with that, I would just like to kind of run you through brief history of our fascination with light. So it's really evident the impact of light that's really an integral part of our daily lives. The earliest human beings, right, were fascinated by fire. So in the prehistoric times, they used fire for their survival. And when burning oil became known, it was extremely transformative, and people used it for nighttime illumination. And this was about 15,000 years ago. So sometime around 7,000 BC or so, different civilizations were really becoming increasingly aware and interested in optical phenomena. And they were using a variety of different types of optical materials like glasses and jewelry. Some ancient philosophers in Asia and also in Greece already knew that light was composed of different colors. So white light is not really white, it's actually composed of different colors. Interestingly, the Greek scholars, sometime around 300 BC, looked to study optical phenomena in more detail, but their understanding was somewhat limited. And the reason was that they assumed that whatever we see around us, vision, is the cause of vision is because our light emanates rays. Our eyes emanate light rays. And they believe that this is why we see things around us. This is obviously wrong. But it would be a very cool superpower to have, right? If you can project light out of your eyes. But starting sometime in the 10th century or so and going into the Renaissance era is when there was some seminal contributions into the topic of light matter interaction. So as we know, Snell's law today really deals with the topic of reflection. There were some famous scientists that worked on the topic of diffraction, which really kind of put forward the theory of the wave nature of light. And even more recently, James Maxwell, for example, provided a very comprehensive summary of the electrodynamic principles that were being developed by other scientists like Faraday and Ampere and so on. And that his formalism really led to the birth of electromagnetism as we know it today. Following that, there were scientists like Einstein and Max Planck who then postulated that light is not a wave, it's a photon, right? So a lot of things have been happening, especially at the turn of the century, but really we don't completely understand light yet. So you all know about the wave-particle duality, and that is as complex as can be. And despite all of this, despite our limited understanding of light, we know just enough to make use of it for some important applications, right? And the progress made towards our understanding of light has also been fueled by complementary developments on new materials, which have been equally important, not only in terms of understanding light, but also controlling light. So several important eras in history have been really defined by materials that were dominant at the time. So names like Stone Age, Bronze Age, Iron Age, and so on really speak for themselves. So we are currently in the age of silicon, dominated by all kinds of fancy electronics, but we are really slowly inching towards saturation in terms of progress. So if you probably remember from some prior speakers in this forum who spoke about the limitations and the importance of Moore's law. So the next generation of materials will really be focused on addressing more limitations pertaining to Moore's law, and that is really to progress towards making devices smaller, faster, and more efficient, right? So with this, we are going to have to address issues like climate change, access to energy, and in fact, there was a recent report in the World Economic Forum that spoke about that mentioned some very important avenues for some next generation applications, and about 50% of them had direct relevance to the next generation of materials. So the open question is which material it is that's going to drive the next big era-defining technological advance. And I hope to talk about a couple of these very exciting materials platforms here. So today we are at a uniquely important period in history where light and matter have applications in all aspects of life, as you know. So optical fibers, which enable communication and internet access. Lasers, for example, have been used in a variety of applications, including manufacturing. You can now print stuff with lasers. You probably have fancy TVs at home, or you're familiar with TVs that use quantum dots in an effort to make the contrast better and also make televisions more energy efficient. And I live in the Bay Area here in California, and it's quite a regular occurrence to see fancy cars like these driving around. And apparently they're driving around to map out roads using radar and LiDAR technologies to really be dominant players in the autonomous driving market, right? So the next generation of cars are going to be self-driven, and light and materials are going to be a very integral part of that particular avenue. But despite all of these advances of late, there is really need for more to do more work. There's room for further fundamental research to really drive next-gen applications, as I'm going to show soon. So I think we should take a little bit of a step back and get a brief refresher of electromagnetic waves. I'm sure you're familiar with the concept of light, right? So light, if we consider light as waves, then it can have an electric component, a magnetic component that's perpendicular to the electric field. And as a result of this, the flow of energy, which is defined by the Poynting vector, is perpendicular to both the electric and magnetic fields. And because it's a wave, it can have a wavelength, it can have frequency. And in general, as you increase wavelength, you decrease energy of the light, of the light beam. There is one very important metric here, and that's the wave vector. It's simply given as 2 pi over lambda, but the real consequence of that of the wave vector is that it tells you about how light propagates in materials. So it tells you about the magnitude and direction of light. And coupled to that, or rather related to that, is the so-called dispersion relation. It's just important to know at this point that this relation correlates the frequency or wavelength of light to some important properties of the material, like refractive index and the speed of light in the material, and the wave vector as well. And you probably know quite a bit about the electromagnetic spectrum as well, right? So on one end of the spectrum, we have radio waves with a wavelength of tens of meters. And this is what is used in AM and FM radios. And as you go down the scale here, we step into the regime of cell phone communications, microwaves, which are on the order of a centimeter or so. And then we can, going further down, we come to the infrared range. And as you probably know, pretty much every body on Earth emits infrared radiation as heat, right? By the way, infrared radiation is on the order of few microns to tens of microns in size in terms of the wavelength. Something that's more relevant to us is the visible light, because everything that we see around is within the visible spectrum. And it's only a very narrow band in the electromagnetic spectrum, ranging from 400 to about 700 nanometers. And going down further, we get into the UV regime and X-rays, which really come down to the scale of a nanometer. So a nanometer is about 1,000 times smaller than the width of a human hair, right? And this really enables applications in medical X-rays and so on. But in general, there are applications that kind of stretch all across the entire electromagnetic spectrum. I want to also give you a refresher on topics like reflection, refraction, which is, again, I'm sure all of you are familiar with. But it's important to realize that as a consequence of Snell's law, light, when it goes from one medium to another, ends up bending or changing directions. And this is really the essence of Snell's law. And interestingly, there's also something called the Fermat's principle, which is less commonly known than Snell's law. And Fermat's principle states that light follows the path of least time, right? So if you want to go from A to B here, Fermat's principle says that you have to go through this line, basically. And it's important to keep in mind that the path of least time is not the path that has the smallest distance, right? And that is because the refractive index is different in material 1 and material 2. Right? So these are two different materials with two different refractive indices. So you can use this particular principle and derive the Snell's law, in fact. So you can just kind of calculate the time for light to go from A to this point, the interface, and then the interface to B, sum it up, take the derivative with respect to X, set it to 0, and you're going to get the Snell's law. Right. So I just kind of highlighted here just to show that it's such a powerful kind of a law, if you will. But as you will see, it really has applications in very important and fancy optical materials. Another area that I want to highlight is the so-called diffraction limit. You may or may not be familiar with it, but the idea is very similar to Fermat's principle. So if you take a beam of light and shine it through a lens, because of this law, okay, the lens is going to focus the light beam on a piece of paper or whatever plane. So the diffraction limit states that you cannot focus the light below about the size of a wavelength. So you can't focus the light to a region that is about λ/2. So that is really the fundamental limitation. It doesn't matter what kind of a lens you have. It doesn't matter how much you polish it. That is a fundamental limitation that is governed by this wave vector that I already mentioned. So typically in normal materials, the wave vector can only propagate with a certain magnitude that is limited inherently by the material itself. And this diffraction limit has very important consequences. This is really the reason why you can't just take an optical microscope and look into atoms or molecules, right? Because with conventional optical microscopy, we come in with light of wavelength 500 nanometers or so, let's say, which puts the resolution limit to about 100 nanometers or slightly higher than that. And what is important to understand here is that it's not that light cannot penetrate through whatever's small spatial scales on the order of nanometers. So if you were to shrink yourself to the size of tens of nanometers and go from point A to point B that is separated by, let's say, 50 nanometers, and the light that's being focused, let's say, is about 500 nanometers, you're actually going to see all of the light going from point A to point B. So the issue is not that there's no light there. The issue is that you cannot collect any information out in the far field. So whatever happens within this 50 nanometer range is all that information is just going to die out within the distance of about one wavelength. And as you go farther and farther and farther and farther, you're going to lose that information. So this is what the resolution limit means. And we'll see a little more of why this is important later on. While we are here, I just wanted to also remind you that the refractive index, right, N is basically tells you how light speeds down or speeds up in a material compared to the speed of light. It can't really speed up, but it can only speed down. And the refractive index is also given as the square root of epsilon times mu. So epsilon is the dielectric permittivity, mu is the permeability. They're both complex quantities. And what they mean is, in a very simplistic picture, they, for example, dielectric permittivity tells you how resistant a material is to the propagation of light. Similarly, with magnetic permeability, how resistant is a material to the propagation of magnetic fields of light. So dielectric permittivity is the resistance to electric fields. Magnetic permeability is the resistance to magnetic fields. While we are at it, I also wanted to highlight some other fundamental kind of effects here. So absorption, you're very much familiar, all of us are familiar with absorption because we see things around us as colors. So the reason we see things is because part of the whatever light goes in is absorbed and part of it is reflected. So whatever color we see is the reflected light, obviously. But you can also envision this scenario in a different kind of a setting. So if you have a two-level system, right? So if you have an atom, for example, an atom has electrons. And if you just represent an atom as a two-level system, so in the ground state, you have all of the electrons in kind of the rest state. And if you supply some energy into this system, and this energy can be in the form of light, it can be in the form of electricity or heat, then this one or many electrons can actually jump to an excited state. And this is exactly what absorption is. Now, on the contrary, on the flip side, there is spontaneous emission. This is exactly the inverse of what absorption is. So if you have something in an excited state, for example, an electron, the electron can decay into a ground state and it emits a photon. And this is the principle behind how light emitting diodes work, or your bulbs or tube lights really work. Similarly, stimulated emission is a little more interesting. So if you, again, have an excited electron and now supply some energy to the system, what you can get is actually two photons. So the photon that you put in and the photon that gets emitted because of this transition. And this is, of course, fundamentally the principle behind how lasers work. So the working mechanism of a laser is a little more complicated than that, because strictly speaking, we should use a three-level system, not a two-level system. But the concept is the same, right? So if you have a material that exhibits stimulated emission, like a laser crystal, so ruby is one very famous example. So let's say we put, in order to get lasing from stimulated emission, we put ruby inside a cavity. And what I mean by a cavity is put it in between two mirrors. So one mirror should be reflecting 100%, and the other mirror should only be partly transmissive. So what happens when we supply energy or stimulate the system is, because of stimulated emission, there's going to be a buildup of photons within the cavity. And because we have two mirrors in the cavity, the photons are going to circle back and forth multiple times. And eventually there's going to be a state where there's going to be equilibrium in the system, right? So we'll have photons coming out in unison. And this is really the principle of lasers. So lasers have three very interesting properties. That is, one, they're monochromatic, which means they emit only one wavelength or only a very narrow range of wavelengths, unlike other light sources. They're also collimated, which means lasers are very narrow and they don't spread a whole lot. And finally, laser beams are also coherent in space and time, which means that they emit photons which are all in phase with each other. So you can just envision, it's like people standing very orderly in a line, let's say waiting for a job interview or something. Compared to other light sources where photons are really helter-skelter, this is like what you're going to find in a bus stop or a railway station where people are in a hurry. So that is really the kind of picture you have photons in non-lasing systems. So by the way, the development of the laser, in my opinion, is arguably the most important innovation in the last 5 decades, mainly because of its reach to many different aspects of humanity. So the original pioneers of the lasers were these people listed here. They ended up getting the Nobel Prize for it. But there were actually many other people involved in the invention of the laser at the time. And if you're not familiar with the story, it's a fascinating story. Um, and it just goes on to highlight the importance of working on emerging topic, fundamental science, and also keep good bookkeeping. So I highly encourage you to familiarize yourself with that story if you're interested. So ever since 1964, from when the first Nobel Prizes were awarded for the lasers, there have been over a dozen Nobel Prizes and over a dozen Nobel laureates who have used lasers for many different applications. And as recently as 2018, when 3 people won, again, the Nobel Prize for their work on ultra-fast lasers. So these lasers can emit pulses that are extremely short, extremely small in terms both spatially and temporally. And as a result, you can focus, you can put in a lot of energy in a very, very small spatial extent. Okay, so we got a little bit of refresher into light, into electromagnetic waves. So on the other side, we know that materials are made up of atoms, and if you zoom into to an atom, you have the nucleus with electrons, and nucleus is really surrounded by many electrons in different levels. So one way to look at inside the atomic structure is through an energy band diagram. So you're probably familiar with the concept of valence band and conduction band. And it basically means that in the valence band, you have electrons that are closest to the nucleus. In the conduction band, you're farther and farther away from the nucleus. So using this kind of a picture, we can categorize all kinds of materials into as being either metals, insulators, or semiconductors. So in metals, there is usually a very strong overlap between the conduction and valence bands. And what this means is that because the conduction band lies so close to the valence band, all of the electrons that are in the conduction band actually participate as kind of free electrons. This is the reason why metals are very conductive. This is also the reason why metals are reflective, because you have all these electrons ready to participate in conduction or any optical processes. So from an optical point of view, metals have a dielectric permittivity that is less than 0 under most circumstances. So let's just keep this in mind for now. On the other hand, insulators, or so-called dielectric materials, have a very large gap between the valence band and the conduction band. And this is the reason why insulators don't conduct electricity, because it takes a lot of energy to pull out electrons from deep within. And this is also the reason why most of the insulators are transparent, because there are no electrons that are readily available to participate in an absorption process. And so consequently, the dielectric permittivity for such materials is positive. And somewhere in between metals and insulators, we have semiconductors that can behave as insulators or metals, depending on how they're doped. But we can really put all of the materials, almost all of the materials that we know, into this kind of a quad chart. So here I'm plotting epsilon as on the x-axis, permeability on the y-axis. So if we have epsilon positive and permeability positive, this is the case, as I said, with most dielectric materials, so most insulators. So materials like glass, water, you name it, and pretty much anything you see around you that is not a metal is going to be in this quadrant. In the second quadrant, as I said, this is where epsilon becomes negative. So this is where all of your metals are with their shiny luster. Some doped semiconductors are also here. But there are really no natural materials in quadrants 3 or 4. There may be a handful of materials in quadrant 4, but there are no materials in quadrant 3. And part of the reason is that it is almost impossible to elicit a magnetic response from natural materials. And this is the reason why the permeability is extremely weak usually. It's almost always close to 1 in almost all materials. So you may wonder, right? So if we have all of the materials that we know in quadrants 1 and 2, what could happen if we can envision or design some materials in these two quadrants? Like what are the possibilities that could come up? And this is exactly the question that a Russian physicist named Victor Veselago posed in his paper sometime in the 1960s, where he envisioned a very visionary picture, and he wondered what would happen if we had control over the magnetic properties of light as well, so of materials. So he wondered if the permeability can also have a negative value. And he postulated that if such a material in fact exists, then the refractive index should be negative. And I can explain this in detail if anybody has questions about this. But if you have both epsilon and mu negative, then remember that you can have two solutions for a square root. It can either be positive or negative. Then just because of how these materials behave, we have to end up taking the negative square root. So the refractive index in such materials, if they exist, should be negative. And this is very counterintuitive because before this, we did not know of any materials that had a negative refractive index. And this also has another special implication. So for a negative index material, then the refraction will also be negative. So if we look at Snell's law, we know that if light comes in from this side of the normal onto an interface, it has to bend away from the normal. This is just a consequence of Snell's law. But if now the refractive index is negative, then it means that the refracted angle should be negative. And this is exactly the concept of negative refraction that I mentioned. So refraction happens on the other side of the normal. And this idea was extremely revolutionary at the time. It was hotly debated. Nobody really believed it was possible, mainly because there were no natural materials, as I said, that exhibited that such properties. So the idea just kind of got buried until about 30 years later, when a British scientist called Sir John Pendry came out with a prediction that one could, in theory, engineer such a material by inducing a magnetic permeability response in materials artificially. So the trick was to engineer the material with some metallic inclusions, and it required two constraints. One, it needed the size of these inclusions needed to be less than the wavelength of light. And secondly, there had to be a resonance in the system. So resonance is quite common across everything around us. So for example, your pendulums exhibit resonance. If you just throw a stone in water, the ripples are a consequence of resonance. And so his idea was to introduce resonance into the system and basically develop a kind of self-capacitance and self-inductance in the system induced by light. And this was a consequence of the well-known Faraday's law. So he argued that when we do this, materials now exhibit a magnetic permeability response, and the permeability can in fact be negative. So after this prediction, not long after this prediction, there was the first experimental demonstration of metamaterials in the lab. So this was done for microwave frequencies. And what is plotted here is just to say that for a normal material, if you just plot the power that is measured from diffraction as a function of angle for a normal material, this should be on the positive side. But for the so-called left-handed material or the metamaterial, you're going to have diffraction on the negative side. So this was the demonstration of the first demonstration of negative refraction. So this really led to the birth of the field of metamaterials, which can be defined as materials that are engineered to exhibit properties that are not obtainable in nature, or that are not attainable in through just constituent elements. And the key here is to design these materials, as I said, in geometry, and also engineer them in a sub-wavelength fashion. So this is very analogous to how the bulk properties of materials are really dictated by how atoms are arranged in the system. So it's very analogous, analogous picture with light. So after this, there were a flurry of completely out-of-the-box applications and phenomena that several people started to envision. So I mentioned about negative refraction. So you know that if you put a straw in a cup containing water, you're going to see the straw that appears bent because of refraction. Now, if you again envision rather than water, if you envision a material with a negative refractive index and put a straw in it, then the straw appears bent on the other side. But more interestingly, several people now started thinking about optical cloaking or invisibility. And this was until then only something that was reserved only for movies or science fiction. So here is one kind of a representation of what happens if you design a material with invisibility properties, so you can obviously see behind it. This is, of course, an artist rendering, but this really got people thinking, right? So if we think about how we see objects, as I said earlier, it's mainly due to scattering or absorption of the object, and this is how you can see something in front of you. But if you design a material out of these so-called negative index materials, then there is the possibility of bending the light rays around the material in both directions. So for an observer standing on this side or on this side, he or she would never be able to see this material because there's nothing that's being reflected or scattered. So for the observer, this object that is placed within the cloak will be invisible. Similarly, the idea of using superlensing was put forward. I mentioned to you this limit of the diffraction limit. So using such negative index materials, it was proposed that you could, in theory, focus light to like infinitesimally small volumes. So this was one way to achieve super resolution for microscopy. So you may have noticed from the structures I showed you that it really seemed too challenging to make such structures, right? Like if you're working with microwaves, as I said, the wavelength of microwaves is, in the order of centimeters. It's not really hard to design materials. So you can do this in your living room. For example, you can just get metallic wires, arrange them in a certain fashion, and that's going to give you a metamaterial. But it's a completely different challenge when you want to design metamaterials for the visible wavelengths, so wavelengths of about 500 nanometers or so. And thanks to developments in nanofabrication around the same time, there were many groups that started demonstrating metamaterials in different flavors and different forms, all with very counterintuitive and very interesting properties. So for example, there was the demonstration of superlensing. So we could now get super resolution with just optical microscopes. There was some lab scale demonstration of cloaking, optical cloaking, and such materials were also used, for example, to mimic celestial mechanics, that is, to mimic the conditions of what could be near a black hole. So all these really fancy applications were now, which seemed crazy a few years before, now seem to be quite possible. But it wasn't all sunshine and rainbows, right? So I mentioned that resonance is one key constraint that we need to achieve negative index materials. And whenever you have resonance, you always have losses. So you can think of a spring. A spring has a damping constant, a spring constant, and that. So if you set a spring in motion, it has to stop moving at some point, and that's really due to the damping coefficient of the spring. Similarly, if you have any kind of resonance, if you have an oscillator, you're bound to have damping, and that is really the kind of the reason for optical losses. So if you design a metamaterial cloak, right, and if you have a lot of losses, the losses would simply translate as heat, and you're going to have thermal radiation, and the cloak would just not work. And that was really the fundamental limitation to why negative index materials could, limitation to why you don't see cloaking out in real life. You don't see people turning themselves invisible. And so in order to circumvent these issues with losses, there were a handful of other predictions. And the idea here was to completely get rid of this resonance. So there were a couple of people that kind of asked this question: if we can get rid of resonance and design the same kind of metamaterials with negative refraction by only looking into the dielectric permittivity properties rather than permeability. So to understand this, let's revisit this dispersion relation, and let's just consider a normal material like glass. So if you have a cube of glass, we know that the dielectric permittivity should be the same in all directions. So if you're in X, Y, and Z, the permittivity should be the same. And the dispersion relation can be kind of modified in this fashion. So here again, omega is frequency, wave vector, dielectric permittivity, and the speed of light. So if we have epsilon X and epsilon Z the same, you can immediately tell that this is the equation of a circle. So the dispersion relation takes the form of a circle. And what does this mean? So if you look at the wave vector is really limited by the diameter of the circle. And I'm going back to what I mentioned about the diffraction limit. This is again the reason why you cannot resolve things that are much smaller than the wavelength. It's fundamentally due to this wave vector being limited as it propagates, as wave vectors propagate in a material. Now, what if we had a material that behaved as a metal in one direction? So if it's a metal, the permittivity should be negative, as I mentioned earlier. But it behaves as a metal in one direction. And what if it behaves as a dielectric or an insulator in the other direction? So which means that the permittivity is positive. So if you were to dive into the material, you're going to see everything around you would be an insulator. And if you're going to swim kind of across the material, everything around you would be a metal. So this was the theory that was put forward by two groups. And now if you put that into this equation, so if one component of epsilon is negative and the other is positive, then this is the equation for a hyperbola or parabola. So what is the consequence of this? So now there is really, at least theoretically, no limit to the magnitude of wave vectors because there's nothing that's binding the wave vector within the system. So in theory, you can focus light down to significantly sub-wavelength kind of spatial domains. And this has many other consequences, right? But the idea that materials that have this property of so-called hyperbolic dispersion have very, very large wave vectors. And they also have a property called high density of states. So they also have very high density of states. We don't need to go into detail about what density of states means, but it's basically this just to say that these materials can support very large wave vectors. So what if, so I mentioned that, yeah, they have large wave vectors and high density of states. So you may ask, well, what is the big deal about that? So there's a very profound consequence. There's something called the Fermi's golden rule, which basically states that the transition rate, and this transition can be anything from spontaneous emission to scattering or stimulated emission, like I mentioned earlier. So the rate or the quality of this transition is actually proportional to the available density of states. So if you have a material, a hyperbolic material with very high density of states, then you can immediately see that you can affect spontaneous emission. You can affect the rate, you can affect the directionality of spontaneous emission. And this was interestingly put forward as a potential approach back in 1946, and it's known as the Purcell effect. So as a fun fact, the whole paper was only about half a page. So this looks like an abstract, but this was the entire paper. So you're probably familiar with reading papers that are a few pages long or tens of pages long. But the idea was so nice that it was only one paragraph, and it's now extremely popular. And I can assure you that people who are designing your latest cell phones and televisions are taking into account this effect of the Purcell effect, trying to enhance spontaneous emission to make screens brighter, to make emission faster, and to make more energy efficient devices. Somewhat relevant to spontaneous emission, as I mentioned, is scattering or reflection. It is bound by the same exact rule. And so here you may ask the question, if reflection can be controlled by a material with a very high density of states, can we actually increase the reflectance significantly, or can the reflectance be reduced to something close to zero? And this was part of the work that I was involved in, partly back in my graduate school days. So here I have to thank all of my previous collaborators, as well as my PhD advisor, for the next few slides that I'll be showing. So, and I'm just showing you just to give you an idea of how easy it is to make these hyperbolic materials and how easy it is to test out these optical properties. So we started out by fabricating such materials in the lab, and all we needed to do was deposit thin films of metal and dielectric that were alternating. And again, we made sure to keep the thickness of the metal and dielectric to about 50 nanometers or so. That was much smaller than the wavelength. And we deposited this material using so-called thermal evaporation. It's very simple. If you, whatever material you want to deposit, you just put it on this target, heat up the target, the material is going to heat up, and then the vaporized material is going to be deposited on a substrate of your choice. So we alternated these structures, and this is the resulting structure did in fact demonstrate hyperbolic properties. This is how it looks. We also designed another complementary structure. I'm not going to talk about this in detail, but just to tell you that even if we have nanowires embedded in some kind of a dielectric media, we can still get hyperbolic properties. Very interestingly, the same kind of material was designed by the famous scientist Jagdish Chandra Bose back in 1897. But of course, this was done for microwaves. So these were about, the wires were about millimeter thick. And he used this particular material as a polarizer. So to change the transmission as a function of angle. And arguably, this was even, you can say that it was even the first metamaterial as early as 1897. But anyway, so here we are dealing with nanoscale materials, but it's very interesting to see the parallels of some very early works in this particular avenue. So what we did once we had these materials, we simply polished them or added some kind of microspheres to roughen up the structures. And we tested the reflection by changing the angle of incidence. So we had a laser that was illuminated on the material, and we measured the intensity of the reflected beam using a simple photodiode, and we changed the angle of the beam. So we basically got an angular profile of the reflectance. And there's a lot of stuff that I'm showing here, but it's just important to kind of keep track of the white and black traces. So the white trace was the unpolished material, which showed a reflection of about 10%. But on top of the material with the scatterers, the hyperbolic material with the scatterers, we can see that the reflection goes down across a wide range of angles, very close to zero. So it was less than about 0.0001%, I think. And this was eventually then referred to as a material that was darker than black, because it just simply absorbs all of the light that you put in. And a very interesting tidbit here it was a story that my former advisor used to tell us. There was a fighter jet in the Soviet era that was shot down by some enemy country. And the reason was that the fighter jet had some water droplets or some dust sitting on top. And so the enemy was able to detect this stealth aircraft because of the reflection from all of the junk sitting on the surface. And that's the reason it was shot down. But if we envision a scenario where we design this stealth jet with hyperbolic materials, with any kind of junk you put in, it's going to be helpful because all of the reflection will preferentially happen into the material rather than going away. So just kind of a brain teaser here for you to think about the possibility of designing such fancy materials. So I spoke a lot about metamaterials, and all of the structures that I showed were bulk. So they were three-dimensional in nature. I also mentioned that it's actually very challenging to design such materials. Typically, if you're thinking about visible applications. So the next big trend in this avenue is in this field is to really go towards making materials and lenses that are thinner and which are easier to fabricate. And so I'm not going to go into much detail about this, but based on the Fermat's principle and Snell's law, as I alluded to earlier, there were some works recently that demonstrated how metasurfaces can be, the so-called metasurfaces can be designed, and they exhibit properties that are very similar to bulk metamaterials, but these are only about tens of nanometers thick. They can simply be deposited on a glass substrate. And this can act as a lens, a very, very thin lens, and it can have many other applications. So for example, making thin lenses, you can think of putting these lenses into the human body for endoscopy. They can go up in satellites where weight is a really big concern. These metasurfaces can also be potentially used in biosensing and bioimaging. And the general kind of broader community of metamaterials can eventually find applications in making better microscopes. As I said, this is one way to really beat the diffraction limit. You can also envision such metamaterial surfaces to control the surface chemistry, which is another interesting area that I did not talk about. And then because of the properties that I mentioned, you can also envision making very high efficient solar cells, high efficiency solar cells, because you have now a way to trap all of that light into a very small region, which is exactly what solar cells need. So with that, so I've spoken a lot about metamaterials. I actually want to shift gears just a little bit before I run out of time and talk about plasmonics. So plasmonics is another very important direction in the area of light matter interactions. And the inspiration for the field of plasmonics really originally came from nanoparticles. So we all know that when a material is shrunk down to the nanoscale, the electronic, thermal, and optical properties of the material change significantly, and the properties become size dependent. So here is an example from 4th century Rome, where the so-called Lycurgus cup, it appears green under normal circumstances, but when you illuminate this material from the inside, it appears red. So this unique phenomenon is actually because of the presence of nanoparticles in the glass that was used to design this particular material. Obviously, they did not know that it was nanoparticles at the time. It was something that was unintentional, but this is kind of a unique property of nanoparticles. We can see something similar in stained glasses that we see in churches. And so this is fundamentally the reason why plasmonics is very important and plasmonics started to develop. It's that these tiny metallic nanoparticles can act as antennas. They're capable of funneling light to a very small spatial scale. So you can have extremely high intensities in a very tiny nanoscale region. And plasmons are essentially collective oscillation of electrons. So you can use light to excite electrons, drive the material into resonance, and this leads to the formation of very high fields. There can be different types of plasmons, but let's not get into that. I just want to mention some very important applications of plasmonics. So we know that lasers can get very bulky. I'm talking about these high power lasers. They can extend onto several optical tables in the lab. But using plasmonics, there's been works that show that lasers can be shrunk to the nanoscale. So you can now have nano lasers. And this is really important in terms of going towards next generation optical devices, making devices smaller and more efficient. You can use plasmonics in solar cells to concentrate light down again and to trap light. You can use it in biosensors, for example, to distinguish two different viruses, because you can make the spectroscopy technique very sensitive by using plasmons as your substrate. In terms of cancer treatment, there is also the potential, for example, to send these nanoparticles into the body and shoot them with a laser beam. And the heat generated by these nanoparticles had the potential to ablate or blast cancer cells. So with that, I'm kind of coming towards the end of my talk. I just wanted to say that there are really many different flavors, many different platforms of optical and nanophotonic materials. I only touched on two aspects in metamaterials and plasmonics. But speaking of next generation applications, I think using these novel material platforms, there's really hope that we can start addressing some pressing challenges in climate change and energy, as I spoke earlier in my presentation. So questions like how can we reduce our carbon footprint? How can we make devices more energy efficient? I think optical materials really hold the key to solving some of these issues. I'm quite optimistic about working in this space. Recently, there have been, just to give you an idea into some potential applications, there have been efforts towards launching these so-called solar sails. So you can now tentatively launch satellites using lasers. And this is really inspired by how sun's light pushes comet tails away from the sun. And it really deals with the pressure of light, and this pressure can also, the force or the pressure of light can also be translated onto materials. So using laser-based solar sails, the vision is really that you get these satellites to travel at about 20% of the speed of light, which is extremely fast. So this is one way for us to get to distant planets that are light years away much quicker than before, and of course mitigate the need to burn rocket fuel. Another very important application using plasmonics is to speed up chemical reactions. So using plasmonic materials as catalysts, we can really enhance the rate and efficiency of things like carbon capture to reduce carbon emissions. I also want to talk very briefly about this very interesting application. So there's been some works that recently show how by just mixing some nanoparticles into water, you can heat water locally, right? So and under sunlight. So what happens is that the nanoparticles, as I said, because of their plasmonic properties, heat up in the scale of several tens of nanometers, and they result in boiling at that scale. So when you have multiple nanoparticles, you can actually get boiling just through solar energy. So this is similar to, using a magnifying glass and killing ants, like I used to do when I was a kid. But if you were more animal friendly than me, you probably just burnt papers or something using. But in all seriousness, using plasmonics is really very similar to this. It's the idea of funneling light into very small volumes and heating up water. And this is one way to actually purify water and also potentially cook food, especially in areas where there's water scarcity and there's a lot of issues in terms of finding good, clean water. There are many other applications, and in the interest of time, I'll just mention that the ultimate goal in electronics and circuitry is to go towards, as I said, much smaller materials, much smaller devices with the goal of increasing operating speeds. And plasmonic materials and other kinds of optical materials really fit the bill in a search for going towards terahertz and beyond. And the next breakthrough, I left it open intentionally just to kind of highlight the fact that doing fundamental science, you may not always have the vision of applications right away. So in many cases, it takes several years, several decades even to have realistic applications. But what is important is to work in something that one is passionate about, and to make sure that whatever we are reporting is what we see. So it's important not to glorify science, but at the same time focus on some fundamental science, and also make sure that whatever we do is interesting and also we are passionate about it, without having to worry too much about the application space. With that, I'm going to open up the floor for questions. I'm going to skip this slide, but I'll really be open to addressing your questions, whether it's related to this particular talk, or whether it's broadly related to any questions you may have about a career in scientific research. Thank you very much for your attention.
Dr. Thejaswi, thank you very much for a very interesting and scholarly talk. Right from the history, you took us to recent developments and what is the future. I'm sure our senior experts are here. Professor Mulimani sir, for your words.
Thanks.
Professor, I'm not an expert. The way whole field is developing at such a rapid pace, it is difficult to keep pace with the developments. And particularly that last slide where you showed, next breakthroughs. Usually in this area of nanoscience, we always say every generation of physicists have to rediscover quantum mechanics for themselves. And we talk about wave function engineering, band gap engineering, and many new things are coming up. Here you have concentrated on photonics. And if you get into the electronics field, what are the various interesting things which are coming up, particularly with regard to this metamaterials and other things?
Thank you, sir. That's a great question. I think going back to what I mentioned about the need to scale down electronics, this is where I kind of see a marriage between photonic materials and electronic materials as we see in the conventional sense. So there is a lot of work now in silicon photonics. So silicon has conventionally been, as you know, in electronic circuits. But the push is now to go towards photonic circuits because obviously using photons, the speed of processing can be much faster at the speed of light. And so the only limitation was the ability to make structures. So the limitation came from the side of nanofabrication. Excuse me. And so now with these materials, I really envision this ideal marriage between electronics and photonics.
Thank you, sir.
Thank you very much, Dr. Mulimani sir. Professor Ayyappan sir. Hello. Ayyappan sir, for your words, sir.
No, thank you. Thank you very much. I know it's such a specialized field, and then I'd like to only say how grateful we are to Dr. Thejaswi for this absolutely enlightening talk and also the opportunities for our youngsters. Thank you very much, Dr. Thejaswi.
Thank you.
Any
Thank you, Dr.
ethical issues involved here, Professor? Ethical issues in the field of nanoscience, are they addressed? Ethical issues.
Yeah, that's it's yeah. I mean, ethical issues are. I would say it's in general something for the science community in general. I don't think there's anything. I can't think of anything specific to nanoscience. Well, yeah, I agree with you. So, for example, putting in nanoparticles into the human body is something, of course, of grave concerns in the medical community. So it is well known that nanoparticles can be very toxic when you shrink the size down to less than 50 nanometers or so. So that can be one extremely important ethical concerns in terms of putting nanoparticles in the body or putting devices into the human body. And quite rightly, people are afraid of this, what the future holds in this direction. But yeah, other than that, I think like in terms of publishing and in terms of reporting scientific discoveries, honestly, as you know very well, ethical issues are kind of common across many different fields.
Very much, sir. Thank you.
Thank you. Dr. B.Y. Satish. Dr. Satish. Hello. Dr. Satish, do you have any question? Well, Doctor, one question. You told about hyperbolic material is darker than black material. That means it absorbs a lot of heat and it becomes hotter than the surrounding place. The question posed by a participant.
That is true. So whenever you have absorption of light, heating is kind of an inevitable consequence of absorption. And as I mentioned, this is one of the reasons why people started moving away from negative index materials, just because of all of the losses and all of the heat that developed in the materials. So hyperbolic materials are not any different in that sense. So depending, if you choose the right wavelengths and kind of depending on the applications, you can really get away with the issue of heating. But of course, when you're talking about, as I said, something like cloaking, if you have any kind of heating, that's already a deal breaker. So now the push is really to make use of heating in not only hyperbolic materials, but also in plasmonic materials, and to really use that to our advantage. So something like what I show here, there's now works where the idea that when a material emits radiation, when you heat up a material, it emits radiation. And when a material emits radiation, it automatically cools down. So this is how the Earth actually cools down during nighttime. So there are now works that are exploring exactly this idea of how to use radiative cooling to design energy efficient windows. So to have simultaneously to let in sunlight, but at the same time, also cool the interiors of buildings and so on. So there are workarounds, but I totally agree. Heating is probably the biggest detriment to the progress in optical materials.
So my last curiosity, these Maxwell's equations we are using, and they remain valid at all levels, or do they need any modification with regard to nanoscale and other things? Because Maxwell's equations are based on macroscopic considerations and things like that.
Definitely, sir. Yes. So fundamentally, they really hold for most of the different optical materials across different length scales. But when it comes to nanoscale optical materials, you're definitely right. So you do have to have corrections to Maxwell's equation. So I spoke about, just to give you an example, I spoke about dielectric permittivity. So for permittivity is of course something that it can be derived from Maxwell's equations. But when you go to the nanoscale, you can have so-called non-local effects. That is, you can't speak of permittivity. So if you have gold, bulk gold, you can't use the same permittivity that you have for bulk gold for one wavelength and translate it down to nanoscale gold. So if you have a 5 nanometer gold particle, the permittivity will be significantly different due to quantum size effects, due to the interaction of this material with its surroundings and so on. So people who do the theory on this definitely do modifications to Maxwell's equations, but ultimately everything starts from there.
Thank you very much. Very exciting talk, sir.
Thank you, sir. Thank you so much.
Mr. Umesh, are there any questions?
No, sir. As of now, there are no questions.
One general questions. Hello.
Yes,
Anthony,
sir.
any question?
No, sir. There is only one question from one participant. It's a general question. How much year of study is required to become a scientist?
No year of study is required. Anybody
Yes, sir,
can become at any age.
Yes, sir. Yes.
Thejaswi sir, very, very interesting talk. Thank you very much for your time. It must be early morning in the US. You took a lot of pains in preparing the presentation and also delivering this talk. I'm sure nobody has given a talk in the early morning like this, especially for academy. You have woken up very early, and it must be 4 o'clock in the morning. Very nice of you. Very grateful to you on behalf of KSTA. It's a very learning experience, not only for students, for us also. Many things we had forgotten, and applications, most of them we did not know. We understood from your talk. We are very, very grateful to you. Thank you very much for this wonderful talk. Thank you very much.
Thank you, Dr. Ramesh. Thank you so much. Yeah, it is a little late for me, but this was very exciting for me to present, and also I hope that I maintained my levels of energy. I hope that I wasn't putting people to sleep just because it's so late for me. So thank you so much.
Thank you very much.
Thank you, sir.
Ayappan sir, thank you very much. Professor Mulimani sir, thank you very much. You are there in every